So we have already talked about how Medawar's theories of evolution posited that the forces of natural selection decrease with age, or as fitness decreases, because the extrinsic rate of aging or the environment starts to play more of a role. And Medawar kind of justified his ideas for the fact that natural selection declines with age and generated this mutation accumulation theory, where at older ages, natural selection just becomes too weak, or it declines with age to the point where it can't eliminate deleterious mutations or deleterious alleles from the population anymore. And those harmful alleles or mutations become fixed within a small, older population due to genetic drift. And this is based on the idea of that genetic determinism, right? So every biological process has a gene that regulates it. And in Medawar's time, that would have meant that one gene could have exerted this harmful effect, causing aging. But if that was the case and it was one gene and this effect was so harmful that it caused aging, it likely would have never made it through natural selection to subsequent generations, right? It wouldn't have been able to allow organisms to survive to reproductive age. Therefore, they wouldn't have been able to reproduce, and they wouldn't have been able to pass on these sort of like really harmful aging genes. And so that idea of mutation accumulation comes into play when Medawar theorized that there's not just one aging gene, but either hundreds or even thousands of genes that kind of contribute in a small, mild, but negative way to aging. And he based some of this on the idea of Huntington's disease and how Huntington's pathogenesis works, which you can read more about in your book. And so Medawar has this idea that the force of natural selection declines with age. And then the next person we're going to talk about, Hamilton, is the one who actually did the math to expand on Medawar's theories and sort of put more weight behind them using quantitation and not just theoretical ideas. And so what Hamilton did is he basically created a variable known as the force of natural selection. And you can see this graph here on the right that graphs the force of natural selection over time on specific functions. So on either mortality or death or fecundity, which is ability to reproduce. Right? And so what Hamilton found when he started doing all of this math is that the force of natural selection actually will decrease after reproduction begins. The force of natural selection that's acting on mortality and kind of controlling death, right, will decrease after the start of reproduction. So you can see the start of reproduction here indicated by the dotted line. And you can see that the force of natural selection before that is at 100%, right, or 1. It's very, very high. So any genes that are involved in determining mortality have a very high selection pressure on them until the start of reproduction. And then after reproduction, those genes, the selection pressure on them actually decreases a lot. And so what Hamilton argued is that the genes that are needed to survive to reproductive age get selected for. And those that will result in an organism's mortality before it can reproduce would be selected against. Meaning that this force of natural selection is really, really high up until the start of reproduction. And that any of the genes that are necessary to actually make it to this dotted line or make it to the start of reproduction, those are what are likely the longevity genes. Because natural selection isn't acting as the organism ages. It's acting before reproduction. And so any selected for genes that confer aging or a long life or age and longevity probably are actually selected for before reproductive age. And sort of based on this idea, you can imagine that there are some people in the population who are able to start reproducing or can reproduce later in life, right? And so in the graph in A, the start of reproduction is somewhere around, 12, 13 years. Whereas in the graph in B, the start of reproduction is around age 20. And so there's been a small subset of people who have genes that allow them to start reproducing later in life. And you can imagine that if the forces of natural selection are acting on these genes here and allowing people to start reproducing later in life, you can actually extend out lifespan by decreasing the mortality rate. And this is a theory of how longevity might have been able to evolve. By sort of acting on these long-lived or late reproducing populations, the forces of natural selection aren't able to act. And their effect on mortality is actually delayed by like about 10 years. And so it's possible that longevity evolved in this way, right? With all of the genes involved in sort of late life reproduction being selected for and pushing that lifespan further and allowing longevity to evolve.